All right, everybody. So sorry we couldn't actually talk about this in person today. Hopefully this video will help you kind of make some progress through the notes that we were going to talk about. We'll definitely be able to talk a little bit about it when we meet next week. So if you don't get everything, don't panic. Also remember that Hannah has some office hours that she's going to hold during our regular class time. So let's get started. So today we're going to be talking about higher order derivatives. And we've already kind of seen this a little bit in when we talked about our velocity and acceleration. So we've decided that a higher order derivative is formed by taking derivatives of derivatives themselves. So basically what we say here is that if I take a function and I can take its derivative, and then I can take that function and take its derivative, and essentially what you're doing is measuring how change changes. So we looked a little bit at the notation. Here we saw that this was kind of an operator where we say, okay, I want to take the derivative of f k many times. Or you can look at it where we kind of put the f up on top. Or instead of writing out k many primes, because that sounds like it would get annoying after about like 3, we can do in parentheses k. So if I wanted to take like the third derivative, I could write f of 3 of x, and then that would be the same thing as doing 3 primes, but they get a little annoying to count. So we talked a little bit about, at the end of class last time, how the derivative can kind of tell us at any point if we have a function that's increasing or decreasing. But what can the higher order derivative tell us, if anything? Well, the big thing here is that it tells us about concavity. So we'll do a quick recall. Recall that concave up meant that the average rate of change was increasing, and concave down meant that the average rate of change was decreasing. And we had kind of a nice little chart about concavity in our notes in Unit 1, so maybe go back and check that if you wanted to think about it. But hopefully you might remember when we talk about concave up, we have a graph that looks like this. And when we look at the average rate of change, we can look at the derivatives at any point. And you'll notice that as I was drawing here, we have slopes that go from very negative to less negative to something maybe like 0 to positive to even more positive. So our derivatives are increasing. So the slopes here are increasing. So then what we'll notice is 3 things. When f of x is concave up, we know that f prime of x is increasing. That's what we just saw in our picture. So then if we know that f prime of x is increasing, then by our argument that we talked about yesterday, we know that that thing's derivative should be greater than 0, because we said that a positive derivative means increasing. So that function's derivative, f prime, should be greater than 0. So f double prime is greater than 0. So just to make sure that we kind of understand the concept here, if I do a concave down function, I can see that my slopes are positive, something less positive, probably 0, more negative, more negative. So the slopes here, oops, I'll try that again. The slopes here are decreasing. So we can make our parallel list here where f of x is concave down means that f prime of x is decreasing and f double prime of x is less than 0. So knowing about the sign of the second derivative will tell us about concavity. So why is this? Well, if we're looking at the second derivative, tells if the first derivative is increasing or decreasing. And that's essentially our definition of concavity itself. So essentially we'll use that same relationship that we know about a function and its derivative, but instead of using it from here to here, we will use it from here to here, which is kind of nice. So that's what we can talk about with higher order derivatives. And we'll see a little bit more of that kind of as we make some progress. But if we're cool with that, we're going to move on to derivatives of multivariable functions. So we decided that our kind of progress for this class was going to be, well, I'm going to do something for single variable, and then I'm going to move it into multivariable right away. We did that with functions in Unit 2, and we're going to do it with derivatives here in Unit 3. So here, we're going to start talking about what's called a partial derivative. So the important part here, really the key idea, is that at this point, we're going to be only changing one variable at a time. So we have to decide which variable we're going to change. We still have this idea of change in input and change in output, but now we have multiple inputs to think of. So the partial derivative says we can do this in either variable. It's the ratio of the change in outputs to a change in one of the inputs. So we will think of it as slope in two directions. So the notation here is a little bit different. We have to be a little careful. If I want to change x, that input, right, the first input, what we will do is we'll make this kind of like weird curly partial d thing here. And we read this as partial f partial x. So it looks a lot like our regular derivative, but we know it's multivariable because we see kind of this curvy d. And if we want to change y, we'll do partial f partial y. So you can also read this as the partial derivative of f with respect to y. So the idea here is we're saying we're going to take the partial derivative of f, and I'm going to be changing y as my input as opposed to x. So we see this in slope in two directions. So if we look at this picture here, at any point, pick some kind of bright color here, maybe pink. At any point, maybe I'll take this top point, I can draw actually two different tangent lines depending on what I'm looking at. Well, here, that's one tangent line. Kind of looks like we're saying we're only going to be changing y. We're going to fix x. It's kind of the same idea that we had with cross sections. The slope of this line is partial f partial y because I fix some value of x and I allow y to vary. So we can contrast that to a tangent line that goes this way. So you can kind of see, if you think about, like, my metaphor is always like make a little hill out of your hand. And if you look at the possible places you can put a tangent line, there's kind of two different ways to angle it. So the slope of that line is partial f partial x, where we actually say we're going to keep y being constant and we're going to allow x to vary. So if we're here, we're going to say, well, what does this look like? What kind of formulas do we have? So it's exactly like what we would extend our formulas from slope. So we remember saying that we do the change in output over the change in input. So if I want to do partial f partial x, then when I do my change in input, I really should have x2 minus x1 in the denominator because I'm allowing x to change. I'll think of those two as my points. And what we'll do up top is the same thing that you maybe would think by leaving y constant. Remember, we're only changing one of the inputs, so the y value has to stay constant. So we can kind of then say, okay, well, if I want to do this for y, we would do, f of x comma y2 minus f of y, I did it again, x comma y1 and we'll divide by the change y2 minus y1. So if you look at this, it really looks like slope in x or slope in y. So here would be slope in x, and then in y would be this one. Where we allow one to change, we keep the other one constant. So those formulas are maybe a predictable way to extend how we have our change in output over change in input. Let's do one more tangent line on our graph here, just to make sure we kind of see what's going on. So if I take this point, I'm going to say, well, let's fix a value of x and allow y to vary. That means I need to be able to draw this line in like kind of the y direction. And then if I allow y to be fixed and x to vary, I'm looking at this. So the slope of this line is equal to partial f over partial y. And then the slope of this line is partial f partial x. So again, when we look at these kind of points, we want to say which one am I fixing and then which one am I allowing to vary. So with this kind of in mind conceptually, we can talk about estimating the derivative from a table of data. So the first thing we did on Tuesday, which was trying to calculate the derivative with a table of data. We can do the same thing with multivariable just by figuring out kind of which way we need to move in the table. So let's estimate some partial derivatives within the table first. So we're saying here we have our wind chill chart. Remember that we have two variables here, temperature and wind speed. And we said we're going to estimate partial W, partial T, and partial W, partial V at the point T being 20, V being 35. So if I look on the table, I find T 20, I find V being 35, and I say, look, I've got that spot 0. So I'll do the first one, and then I'd like you to kind of pause, see what you can come up with for the second one, and then see how you did. So if I want to estimate partial W over partial T, I want to allow T to change and have see what the effect is on the wind chill while leaving the wind speed at a constant. So that means that we're going to be moving in this row one of two directions. Either we'll move over to 25 or we'll move over to 15. So again, we want to keep our wind speed constant, which means we're going to be staying in the same row. But then we'll say, okay, we're going to allow temperature to vary. So I get to pick. Maybe I'll say we'll look at the temperature going from 20 to 25. So I'm going to write this in all the generality for the formula. We'll say the wind chill when T is going to be 25, V being 35, minus the wind chill when T is 20, V is 35, over 25 minus 20. So we've left 35 alone, and we changed the temperature to go from 20 to 25. So if you look on this chart, what we've really done is estimated it in this direction. Excellent. So from here, we say, well, the wind chill was 7 here, 0 on the chart, over 20 minus 25, which is 5, which means we have 7/5. I'm going to say degrees felt over degrees actual. Because you'll recall that when I look at the temperature, it's also in degrees, and the wind chill will be in degrees. So that's kind of our good units here. So why don't you go ahead and take a second, try to calculate in the same fashion partial W, partial V. So if we're going to try to calculate partial W, partial V, I would say if I look at the column, maybe I'm going to change my wind speed from 35 to 40. So then for this one, I'll do it in a different color so we can kind of tell that something is different. Now I'm going to move down the column. partial W over partial V. And I'll say it's the wind chill at 20, 40 minus the wind chill at 20, 35 over 40 minus 35. So again, I allow temperature to stay fixed and I allow wind speed to vary. We'll notice that this is -1 minus 0 over 5. So it looks like I get -1/5. Maybe I'll say degrees felt over miles per hour because that's our units for wind speed. So that's a way that we can estimate the derivative by looking at a table. What you'll notice is if you kind of remind us back over here, when we did this in a table the other day, we went kind of either this direction or this direction and allowed those things to change. Really what we're doing is the same thing, just now in 2 dimensions. Am I looking at changing in a column or am I looking at changing in a row? We just have to be careful about what's staying fixed and what is going to be able to vary. So we also talked about how a multivariable function has a contour plot, and we're a little bit familiar with these. Here I have temperature and wind speed, and you'll notice that 2035, that spot that was 0, is right in the middle here. So I want to try to estimate partial W partial T and partial W partial V at that same spot. So I already have one estimate in mind given from the table. What can I do from the contour plot? So again, I'll do the first one and then I'll have you hopefully try to do the second one. So I'll do partial W partial T. I think I used orange for that one last time. So when I want to do partial W over partial T, I want to leave my wind speed constant and allow temperature to vary. So maybe I look at that. Well, if I allow temperature to vary, what I'm doing is looking at a horizontal line while leaving V fixed, which means I don't move anything vertically. So if I'm here, maybe this is 24. I don't know. I just have to be able to estimate. So it looks like a 4-degree change in temperature allows for a 5-degree change in wind chill. So I notice this because I'm looking at 5 minus 0, so the spot that we are at, then go all the way up to 5. And the numerator here is 5 minus 0. The denominator would be 24 minus 20, because that's how much I changed in temperature. And again, I just get to estimate, so I can kind of do what I can. And I get 5/4. So go ahead and take a second, knowing what you know about trying to leave temperature constant and fixing or changing wind speed, what can you do to estimate? All right, so if we're here, I want to try to do wind speed. Maybe I'll go back to blue. It's very McAllister colors. So if I want to do partial W over partial V, I'm going to change wind speed by some amount. Now, I don't have to go all the way up to the contour line, and actually if I even tried to reach -5, it looks like I'm going to go way off the chart up there. So maybe I'll just try to go this far. Looks like maybe I'm at 37, 38, something like that. We'll say 37. We'll say 38. I'd say it's a little bit over half. And then it kind of looks like if I were to trace a new contour, maybe this is just -1. So in terms of changing my temperature, or changing my wind speed by 3 miles per hour, I really only changed my felt temperature by 1. So this actually kind of equates to what we tried to do on the table if we think about a contour plot as kind of like an infinite table, which we had talked about before. Saying, how much can I trace? Try to estimate what changes here. Remember, we read the numerator off of the contour plot, and we'll read the denominator by changing whichever variable we're looking at, either t or v. Excellent. So now we have these kind of two guesses. This is going to be about 1.25. This is going to be about negative 0.33. And I think 7/5 is going to be 1.4. And here we're looking at negative 0.2. So we have a couple of different estimates. One thing to kind of give yourself a mental check is that we'll notice that that partial w, partial t is positive, and partial w, partial v is negative. But this makes sense. We've kind of talked about, particularly when we went back and did cross sections, that it should be that the wind chill decreases as wind speed increases. And that's why we get a negative derivative. And similarly, when temperature increases, our wind chill should also increase. So everything that we want to be able to say about the partial derivatives, things that we know about increasing and decreasing, does hold for partials. So this would be increasing, I'll write this out, with respect to t, and we'll say that this is decreasing with respect to v, because it's negative. Same thing with the thing above with its positive. All right, so now that we have some estimates, what did we do next in terms of single variable? Well, we try to push these small subintervals together. So when we have a formula, and we do, we can do a process that's similar to what we did with single variable. So this code should look kind of familiar. I'm going to claim that the code below estimates something, partial w, partial something, when t equals something and v equals something. So what I'd like you to do is try to think about what we think this is going to estimate. The clues you might want to think about are, where do we vary, or what do we allow to vary, what do we hold constant, and how can I tell what point we're trying to calculate at? All right, so if you looked at this function, maybe we'll do the annotation just like we would do in class. The first one makes the function. We've got to pass it into RStudio somehow. Excuse me. So we pass it into the function here. And here, this is going to be our small subintervals. That's saying how much are we going to let the interval vary. If you go back to the first day that we did this, you might be able to check in with the code if that line isn't familiar to you. So really, I haven't actually answered the question above yet. I have to start looking at the data here. So what do we notice? Well, the first thing to notice is the order of the variables here. It's t and then v. So when we're looking at the variables in our derivative, this is t and this is v. And this is t and this is v. So I notice that I'm varying v, meaning that I am allowing v to change by adding in that y. If you look between those two differences, the negative 11 stays fixed. So if the negative 11 stays fixed and I'm allowing the 3 to vary, then we're going to be estimating partial w, partial v, when temperature is negative 11 and wind speed is 3. And we get those numbers by looking at the derivative itself. So in words, what the code does, it says, builds a function, creates a list for subintervals calculates partial f over, not f, partial w over partial v by changing v and having t stay fixed. So kind of a recall from when we talked last on Tuesday, we said if we have every possible point in between, I can then make my change in input as small as I want to. So I'll push those 2 points together to be very, very close, and then we will be able to get a better estimate for the derivative. And just as a reminder, when this gets a little bit stable, meaning, I stop seeing so much wild changes, I'll probably have my partial derivative. I would say it's probably about like negative 2.572. After that, we can talk about, further out decimals. So that's what this code does. So with that in mind, what I'd like you to do is try to estimate at the point that we've been working with so far. So you'll notice that we have partial w, partial t, same thing, at that same point. You may want to use the code that's up here. So maybe try to keep an eye on that, program it in, see what happens. Hopefully, if I can get this to work, we will be jumping over to RStudio. All right, everyone. So now we're going to be talking about coding up the estimates for partial w, partial t, and partial w, partial v at the point that we care about. So we see RStudio in front of us, and I'm going to create a code block. And just so that I don't have to actually type this function out in front of you, here I have this w make fun, and here's our wind chill function. You'll notice that I have all my stars in here, carets, and I have parentheses around my exponent so that it knows that it's not just 0.1 that I'm doing for my exponent, but 0.16. All right, so in terms of being able to code up the derivative here, the next thing I want to do is make a sequence of small subintervals. So I like to do mine, maybe I'll do 0.1, 0.01, 0.0001, and you might be very well saying to yourself, well, Kristen, these aren't the ones you have in the notes. I just need 1. Okay. I just need to have a sequence of small ones so that I look for that stability behavior. Remember, when we get our list out, we want to figure out kind of where it becomes stable. So the next thing I do is I make what we will call our difference quotient, or that fraction of slopes that we tend to do all the time. I'm going to say, because I'm looking at partial w, partial t, and partial w, partial v, I'll name them these things instead of just d. Then I can kind of do them both at the same time. And it's going to be equal to the fraction of w at, well, I'm going to look at 35, minus w at 35 divided by y, and I will bring the same thing down. Now this isn't done, and it's not correct the way I have it. What I need to now argue is, where should I put the plus y in this first thing? Do I put it next to the 20 or do I put it next to the 35? So in the first one, I put it next to the 20. Because this is partial w, partial t, the first, what we will call an argument, is t, because we see it right here. So that's the thing I want to vary. So then the second one, I will do plus y here, next to the wind speed. So the last thing that we have to do is have it print our lists. And as long as I can keep them straight, we'll print them both at the same time. So hopefully this runs, and it does. At these partial derivatives, we're definitely getting that stability behavior, negative 1.22 or negative 2.2. And here, well, it's actually completely constant. That's okay. That's actually correct. Because if you recall, when we did that modeling activity about wind chill, we said, why is the cross-section linear? Well, it ends up being linear because we've got it linear in T. So this totally makes sense in terms of our stability. So that's the way we will code this up. The big differences between the code that we see in the notes and the code that we have here is that we have a make fun, where our function is, I can do any kind of sequence of small intervals, and then I have to remember where to put the plus y depending on what I'm looking at. If I'm changing v, I put it next to v, and if I'm changing t, I put it next to t. So from our RStudio code, we saw that partial w over partial v was approximately negative 0.22, and partial w partial t was 1.38. So the follow-up question here is, which estimation method worked better? Table or the graph? So let's go back and kind of remind ourselves what we were at. So if we were estimating from the table, we got 1.4 and negative 0.2. Here, we got negative 1.25 and negative 0.33. Kind of looks like the table was better for both. I would say because we had actual numbers versus us trying to do it from actually from the data or on the contour plot. All right, so just to recap, we've gone through 3 different ways to estimate the partial derivative. We went from a table, from a contour plot, and using RStudio. And each of them kind of have their merits and their kind of demerits, I guess. So let's do an application. For all of you chemists, we're going to be talking about the ideal gas law. So in chemistry, we have this ideal gas law. You've probably seen it before. You've probably called it PivNerd, if you're like me. Now, just as a quick reminder, PivNerd has to do with different gas concepts. This is the pressure. This is volume. N is the number of moles, meaning how many actual gas atoms do you have, or gas molecules. R is a universal gas constant. So again, just a number. And T is our temperature. So this is definitely a multivariable function. It can have a ton of variables. Often we're going to have some things that are constant, definitely capital R, and usually probably N. I'm going to keep the number of moles consistent. I'll probably then allow P, V, and T to vary. So from here, what we're going to do is think about working with our partial derivatives. Here's the example. So say we've got the following setup. We've got this container of gas, fixed number of moles, airtight movable lid with a weight on it. Container is suspended over a Bunsen burner. Essentially, the idea is we can change pressure, volume, and temperature. So I could change the volume by allowing the lid to expand or contract. I can add more pressure by adding a weight. I can work on the temperature by heating it or cooling it down. This might not necessarily be super chemically accurate, but do your best. So here, what I have done is made a plot of temperature as a function of pressure and volume. So if you look at the plot, we have pressure in atmospheres, volume in milliliters, and temperature in Kelvin. So you'll find pressure on the bottom, volume on the y-axis, and temperature in the middle of the chart. So for the processes in parts A through C, literally this list over here, I want you to do the following. Draw a path on the graph that kind of sketches the same idea of what's going on in the system. The second thing I'd like you to do is find the final temperature, pressure, and volume, and then find the rates of change of the changing quantities with units. So I will do the first one, and then I'm going to ask that you try B and C. So, starting at 50 milliliters, 2 ATMs, lock on the lid, and heat the gas. So, 50 milliliters, 2 atmospheres. we're looking like we're about here. Lock down the lid and heat the gas. So I'm not going to allow the pressure, or I'm not going to allow the volume to change. I will allow the pressure to change. Heat the gas to 125 Kelvin. So I need to get this to 125. Maybe that's about here. So then, oops, doesn't look like I have a straight line. Again, all we're needing to do here is estimate. So here's the path. We start from here, and we move along this direction, heating the gas to 125 and allowing the pressure to change, but not the volume. So if this spot is pressure equals 2, volume equals 50, temperature is a little bit hard to estimate because we don't have a lot of data. Maybe I'll say that my temperature is 50 Kelvin. We're not sure, but we can do an estimate. Then over here, my pressure looks like it's 6, my volume is still 50, and my temperature is 125. So that's parts A and B done, or 1 and 2 done. Now, I need to figure out the rate of change of the changing quantity with units. I think there's some argument to be had about what is the output of the change and what is the input. So basically, what do I change versus what changes in the system? I would say that I probably change temperature because that's where I know I'm going. So I'm going to do partial T on the bottom because that's the thing I knew that I was changing. I then say, well, what changes? It's definitely pressure. We don't change volume, so I'll do partial P. Oops, that's not what I wanted to do. All right, so you have partial P, partial T, and the way we'll calculate this is 6 minus 2 over 125 minus 50. So it looks like we've got 4 over 75. Quick units check. Temperature will be in Kelvin, and pressure will be in atmospheres. So that's what I'm looking for here. Try to do this for B and C, and definitely notice that here, the temperature remains constant. So you're going to have some type of different path, and you should be careful. So this is what I'd hopefully like you to come in with on next Tuesday. But again, do your best. We'll be talking about it a little bit then. I hope you guys have a good weekend. Thanks for being patient with me and trying out this new thing. Let me know if you have more questions. Definitely toss me an email, and we will catch up with you later.